It looks like we're ready to begin. Welcome back, folks. Hopefully we get some others that join in a few moments, but I appreciate your being attentive and punctual. Any questions at all before we get started? Okay, well, just for a quick rundown of our announcements, our quiz number 7 is going to be due Wednesday, and we'll post one more quiz on the end of this week to be due the next Wednesday. Then, with what's going on next Wednesday, we have our third exam. This one's only going to go up to section 4.1, since we didn't quite get to the end of that section last Wednesday. And as usual, the typical materials that you would expect are posted down below. We have the formula sheet that's going to be the last page on exam 3, as well as 2 versions of the sample exam problems. Version 1 is just brand new problems that are fresh, and version 2 are other brand new problems right out of the textbook. So that's what we have going on so far in the week. That means this week is a pretty normal week. We're just going to work through these 2 sections, probably start section 4.6, depending on where we end up. Then when we return on Monday of next week, the 11th, that could be our second time, or looks like our third time, we'll do another impromptu student-led review session. So take a look at these documents here over the weekend. I'll probably mention this again as a reminder, and come back with questions on Monday, and we'll spend as much time as needed going over the review problems that you suggest. Well, that's our plan so far. Any questions at all before we go back to section 4.2? Okay, well, let's take a look at about where we left off on. We were talking about concavity, whether these things are going to be, a curve is going to be concave up or concave down. And we have our core definition of what we meant by concavity. We say something is concave up if the graph lies above all of its tangents. So the graph is y equals f of x in red, and here it's concave up because any tangent line you put, say visualize a tangent line here or a tangent line here, the graph of this y equals f of x function is above those tangent lines, making it concave up. But if you go across an inflection point, it switches to concave down. And we said it was concave down in this location only because the curve is now below all of its tangent lines. And where it makes a transition, that's the inflection point. Now, this is all just looking at it graphically. We don't try to solve for the intervals of concave up, concave down by just imagining the tangent lines. It's extremely imprecise. So instead, we went to the concavity test. It tells us if your second derivative is positive, that turns out it's the right condition to force your graph to be above its tangent lines, which means concave upward. If the second derivative is negative, then we'll have concave downward. So to apply this test, we have to calculate the first derivative. That wasn't so bad. Here it is, the first derivative. We had to use the chain rule in the logarithm function this original provided. But then you have to go up to the second derivative. So we took this function here, differentiated it again using the quotient rule. That's the setup on this line. And then everything else continuing all the way down to this step. I guess it keeps on going. All the way down to this step is when we set the derivative equal to 0 and we solved it. We found out this second derivative here in its most simplified form will have a 0 at 0, -3, +3. Those are the critical numbers. And now we're just going to cut up the real number line, use this test again to find out where it's concave up and concave down. So that's just talking through the problem. Any questions at all in the process so far? Okay, this one's really long as a problem only because it was a harder derivative. I felt like we should do a harder one on these notes, not make every problem a really fast derivative. But once we get to this portion, I think we use this color as well, we have 3 different critical numbers, so we go to the real number line. This time we make 3 cuts, so there's going to be 4 portions of the real number line. A cut at -3, 0, and +3. So that's where our critical numbers end up. Here's the 4 different regions we're going to produce. an infinitely long one going this way, two finite regions, and another infinitely long one going that way, off to the right. So the last thing we want to take a look at is the second derivative in both cases. Let's just put it up here, f double prime, again and again. Our goal is to determine, is it positive in that region or negative in that region when we wrote down those four f double primes. So next thing we're going to need is our second derivative f double prime in its most simplified form. Hey, this looks like it's actually in view. That's this right up here on the top. Well, this is the analysis after you find critical numbers by setting the second derivative equal to 0. Next steps we take is take just specific test values in every one of those regions and find out the sign of the second derivative. Any questions so far, folks, to this stage? Okay, well, where the red dot is, probably the easiest number to pick for a test number would be -4. And now this work is a little bit tedious, but we're plugging -4 all the way up here into the second derivative. What makes it a little bit more tedious this time is that second derivative is just big as far as functions go. So f double prime at -4 goes like this. First, where the red dot is, we have 4. -4 squared, so that's going to be positive. Move over here, -4 squared plus 9 is just a 25, positive. -4 here will give us a -1. -4 here is going to give us a +7. And finally, -4 in the denominator, well, it's all positive, but let's just write it out just for the sake of completeness. That would be -4 to the 4th power plus 27 to the power 2. So looking at all of this, this whole thing becomes negative. That's because this negative right here, it becomes squared, so it's +16. That's the only negative sign that survives. So we get to say less than 0. So we've got less than 0 in the first region. And now we just keep on going, testing more and more values. There is a shortcut to this. So if you're curious about the shortcut, let's add another pen just to describe it. Forgot how to do that. Add pen, there we go. Let's go with, I'm not sure what a good color is. Indigo sounds about right. So when we look at these critical numbers, not all of them are really created equal. For example, this -3 critical number came from right here. And that group had a degree 1. So we'll say these two, oops, let me fix the pen, have odd multiplicity. There we go, sorry about that pen. Odd multiplicity. This one, where we set x equals 0 as a critical number, it came from that, 4x squared. The power on this one is 2, so we see this, say that one has even multiplicity. So something kind of miraculous happens if you are thinking in terms of multiplicities. Again, -3, +3, they're odd, because the powers here and here are both powers 1, making them odd. So we had an odd multiplicity over here, and we said less than, our prediction is it's going to change direction right here and become a greater than. You might notice that happens on essentially all of our problems whenever we're doing this analysis. If it's less than, the next interval is greater than. But that one is an even multiplicity, 0. If you have an even multiplicity, one thing that's kind of amazing is sign doesn't change. So it still is greater than 0 across this one. At 3, we're hitting an odd multiplicity. So the direction on that one would change. It'll go to less than 0. So again, it's kind of a weird number game. If you have even multiplicities, the signs stay the same direction, and odd multiplicities means they change. But if you're not a big fan of that, in all honesty, it's just as fast to grab a number. like 1, throw it into your second derivative and just test out the sign. So let's maybe try it a couple of them just to see if these predictions come out correct. So plug in 1, we have f double prime at 1, which means this is 4 times 1 squared, just a 4. This group is going to be a 10. We're throwing in 1, so now we have a 4. And then a 2 on the next group. Down below, it's going to be just a 1 plus 27, so it's a 28 squared. So sure enough, if we look at this, that's a positive value for sure. And there's nothing in here that came out negative. So it makes sense it has to be greater than 0. But it's a surprise that it doesn't change directions here. Again, the reason for that is because of the even multiplicity across 0. But let's just throw in another value. Oh dear, let me look at this carefully. If I want to throw in 1, that's a reminder that over here, we called that 1. That was really a negative 1. Sorry for the confusion on that, if you're wondering what in the world Mike's doing. Should have been negative 1 across 0, but you know what? If you make that negative 1 right here, and imagine negative 1 going inside, that's negative 1 squared. It's still 1, so you still have a 4 here. Putting negative 1 there doesn't change anything. That's still 9 plus 1, so we still get a 10 right here. Negative 1 right here does give us a 2 on the next group, so that's a correction we should make. Oop, didn't need to do that though. So finally, correcting those weird steps, negative 1 here gives us a 2. Negative 1 here will give us a 4. But still, it's positive. And we found out that f at 1, f double prime at 1 rather, is also positive. That was the value we did here before the correction. So last one, plug in a 4, and let's just see what we get for there. Let's scroll down. Oh, I can't scroll down too much. We have to see the original function as well. Let me just zoom out a touch, and we'll zoom back in afterwards. So last test value is at 4. Evaluate f double prime at 4, which means we're going way up here, just throwing in a 4 everywhere. So first it's 4 times 16 times, over here that's 4 squared for a 16 plus 9 for a 25. Almost feels like deja vu when we did it at negative 4. Here's where the changes are. 4 here is a 7. 4 in the next group will be a negative 1. And the denominator is some positive quantity, 4 to the power 4 plus 27 squared. The big punchline with all this is, after I get the concavity test out of the way, whole thing is negative because of where the red dot is currently. That's the only negative factor. So the whole thing is less than 0. So this pattern really did hold out, and we did it in 2 kind of ways. We did it with the shortcut, analyzing multiplicities, and by just doing test values. Any questions whatsoever, folks, producing this analysis?
So is like that the final answer for everything, or what parts are all like the final answer for the question?
The final answer is where we go to say the function f is concave up on this interval and concave down on this interval. So we're like 1 step away of making that ultimate conclusion. Essentially, we're just going to use the concavity test and say which intervals are concave up, concave down. Other questions at the moment? Okay, thanks for asking about that question, Alejandra. One thing that's kind of rough about such a long problem like this is, honestly, it's hard to keep the original instructions in our mind the whole way through. Original instructions were, find the intervals where f is concave up, intervals where f is concave down. So we did all of this work. Most of that right there is just simplifying the second derivative. We came down here and gave this analysis. So finally, here's the big punchline. Concavity test kicks in, and we can now say, on this interval, it's going to be concave down. So I'll use CCD as a shorthand for concave. Down for when it comes up. And let me erase that spot, or that's going to drive me nuts. then here, f double prime is bigger than 0. So in the concavity test, where that occurs, we say it's concave upwards. So likewise, we'll say CCU on this one for concave up. It's concave up again on that next region. Finally, concave down on this region here, where the derivative came out negative. So we're essentially done with the concavity test. We just need to say our answer. So here's the final answer to this long part A. The graph of f, let's say y equals f of x, is concave up on, let's take a look. This interval here, and where the red dot is, and the very next one. The first interval goes from -3, 0. Notice we have to actually use open parentheses like this. Because at -3, the second derivative is 0, not positive, so there's no concavity when the second derivative is 0. So it only goes from -3 to 0, excluding the boundary points. Then it's concave up again on this new region, so we have to say union 0 to 3. It's not correct to say from -3 all the way to +3, because we have to exclude 0 in the middle, in other words. But now we can say, and is concave down on -infinity up to -3. That's where it was less than 0 here for the second derivative. Union from 3 off to infinity. And because there's so much work on this problem, let me do the box your answer strategy just to emphasize that right there is finally our ultimate answer to part A. Well, any questions at all, folks, working with the concavity test? Okay, now that we have the concavity test down, next thing we're going to look into is inflection points on the graph of f. This is kind of a tricky process. The definition is an inflection point. Let's just write it here into the notes. Inflection point, or point of reflection. This is a point on the graph of y equals f of x, where concavity switches directions. So we're looking for now points of inflection. Concavity switching directions, we mean where it switches from concave down to concave up, or vice versa. But this is a good way to think about this. It's a point on the graph of y equals f of x reminds us that inflection points look like this now. We put in a number as our first coordinate. Let's take a look at our analysis. This was concave down to concave up. That means at -3, we switched concavity. So we put in -3, f at -3. So the point, the fact that we have an actual ordered pair, that means we have a point that we're specifying. The fact that there's f at -3 reminds us this is a point on the graph of the original function now, y equals f of x. Here's where it gets a little bit tricky though. We said it's concave up here and then concave up here. That means 0 is not an inflection point. Concavity never changed on this graph. And that's weird enough, we should say it here down below. Let's say it this way, 0, f of 0 is not an inflection point. Since y equals f of x is concave up to the left and right of x equals 0. In other words, there was no switch of concavity when x was 0 up here on our sign chart above. But on the next one, we did have a switch. We're concave up to concave down. So at x equals 3, that's the x coordinate for the next point of inflection. So we go down here and put in 3 f of 3. And we have to evaluate both of these second coordinates here, f of -3, f at +3, and see what they come out as. Any questions first to this point? Okay, so again, it's a really long problem, and another danger of such a long problem is we haven't seen the original function f of x in some time. Up above here, that's the second derivative. We don't use that one at all because we're talking about an inflection point on the original graph of f. So for the same reason, we skip this one, f of x. We're using that function, the very original one. Might as well just pull this one as a screenshot temporarily. Let's come down here, hide the other extra stuff we don't need for the moment, and use that function there. So we're plugging -3, +3 into the logarithm of x power 4 plus 27. And the good news about that, let me grab a quick calculator, is if you're doing x power 4 plus 27, doesn't matter if it's a -3, because or a +3, you're getting the same value out due to the even exponent. So in either case, at -3 or +3, we're taking the natural logarithm of 108. So here are the inflection points. -3, natural log 108, and +3, natural log 108. So that's how we get the intervals of concavity exactly and find the exact locations of the inflection point. Just essentially taking derivatives, solving them, and doing a number line analysis like this up here. Any questions whatsoever, folks, on our conclusion now on example 2? Okay, these are really pretty long questions, and now that we're in section 4.2, these are things that will end up on the final exam. Even though the final exam is a 2-hour exam, I still tone down these kind of questions. Occasionally in class, we do a longer derivative like this one, just for the sake of practice. But in an exam setting, I would have to tone down that function just to make it a little bit more algebraically quicker to get through, get to the main parts, the calculus, in a real exam setting. But this is pretty helpful in case some of the problems do get a little bit longer in the homework as well. Well, we're interested in concavity, not just because of finding inflection points and those kinds of things. Our major goal here is really about optimization. So the second derivative test for concavity eventually turns into the second derivative test for local minimums and local maximums. But the way it does that is actually kind of tricky in a way. In fact, if you look at these notes carefully, and you're like me, you might feel like there's a typo here. Notice the mismatch in directionalities. Second derivative positive, but we said minimum. That feels weird, incorrect, like there's a typo, but it's actually correct. And in the other direction, this one we said second derivative is negative, yet we have a maximum. Again, that feels so weird, it deserves some extra justification before we even try out this test. But this is the major reason why we've talked about concavity, to get to these kinds of ideas here, second derivative test. Well, to illustrate the second derivative test, let's put down an example function. Let f of x equal, and I have one here in my cheat sheet, it's x times natural log of x squared. So that's the function we want to investigate. Let's do a really quick graph on that. X, natural log x squared. Because of the natural log x in the problem, the domain starts at 0, excluding 0 as well. But notice we have looks like a local maximum right around here, and we have a local minimum right around there. That's the kind of graph we wanted to see for this example. So let's make this our screenshot. Okay, we've got a function. This is now y equals f of x, the curve in blue. So taking another look at this, let's see what all these moving parts are. First, when it says f prime of c equals 0, this means our first step is find a critical number. Well, let's say this a little bit better. Find the critical numbers of f. So that's what that's asking for. But when the derivative comes out as 0, that means the tangent line is horizontal. So we have a horizontal tangent line here. This is the location where the derivative is 0. And a horizontal tangent line here. So this is another location where the derivative comes out as 0. Now, looking at it further, let's focus on this element. F double prime at c greater than 0. Another way to think about that is f double prime x bigger than 0 means f is concave up. Concave up because of the greater than 0. But if f is concave up, that means something else entirely as well. So f is above its tangents. All of its tangent lines in that region. So let's take a look at where it would be concave up. F has to be above the tangents, and it looks like in this region, we have concave up right here. So let's say about here, I don't know the exact location of the flexion point. We'd have to solve it ourselves. It looks like from here to here, we have concave up. By the similar token, let's take a look at this information. F double prime at c less than 0 means f is concave down. Let's say that again, just connecting the dots. F double prime at x less than 0 means f is concave down, and that means something else entirely as well. So f is below its tangents. So where is it concave down? The curve has to be below its tangent lines. It looks like in this region, we've got concave down. So let's say from about here to here, oh, let me try a little bit better. I can't put anything out here. The domain starts at 0, excluding 0. So from this region here to here, about, we have concave down. Well, any questions so far, folks? Talking about these steps, these connections with concavity? Okay, so thinking about the concave test one more time. First thing you need is a critical number. Find all the critical numbers of the function. So you take the first derivative, set it to 0 and solve. Then, if this happens, if your function at the critical number, your second derivative is positive, so that you're concave up, that happened here, you get a local minimum. And looking at the graph, that actually seems correct. F at c is a local min in this problem. Oh, I just saw a chat go by. Dennis says, how can you have concave up on two intervals in a row like on the previous question? And this question looks like one interval is in one direction. Well, that's a great question. Let's maybe take another look at it. You're referring to this question here. One thing about concavity is anything can go. It could be concave up on every single one, concave down on every single one, or alternate and sometimes fail to alternate. But we said concave up from -3 to +3. Let's see if we can justify that. You have to put the original function into a calculator. So let's put that one in. Natural log x power 4, almost had it. This is a slightly different version of the logarithm function. X power 4 plus 27. And we're interested mostly in the domain relative to your question you asked Anna. from -3 to +3. So let's bake that into the graph as well. So -3 less x less than +3 is our domain. And when you say 3 tangents, well, you could put as many tangents as you would like on a graph. For example, let's pull this one up as our graph to investigate. So here's that graph from -3 to +3. And we can put as many tangent lines as we like on this. For example, let me pull that up. I forgot I have to use the annotation tool now. There we go. Oh yeah, so this one had just one horizontal tangent right over here. So that horizontal tangent can be visualized this way. And we have another horizontal tangent going this way. Another horizontal tangent going this way. But for every single point from here to here, it looks like the graph is always above its tangent line. The only single solitary point that's out is the one at 3. But what happens at, the one at 0 rather. That was the interesting point. But when you plug in 0, you get the second derivative itself equal to 0. So that's one point that has no inflection. Sorry, losing track of my windows there. Okay, so where is that concave down at? Concave down would be if we extend the domain and go to the left of -3. Remember, we were just doing the 2 concave up regions. And this chart says if we go to the left, we should see concave down. Or if we go to the right, we should see concave down again. So let's check that out. I keep clicking the Moodle website. That's the wrong one to click on. So if we go, say, a little bit to the left, we said that's at a point of inflection, -3, f at -3. So let's now say we go over to -5 now, or maybe -7, see what happens. So once we go beyond, maybe even further, just to see if we can visualize it better, way out in this region, if we put a tangent line, say, maybe over here, oh, and I got to use this annotate, put a tangent line here, and it looks like around this region, any tangent line you put down, the graph is going to be below its tangents. Kind of hard to plot those. Whereas over here, it's above the tangents. So we've got concave down as soon as we go to the left of -3. Looks like it's about right. Hard to visualize, but the graph is below its tangents. So here's -3. We go to the right and it's always concave up, except for that one point at 0. We have concave up in 2 different regions. Glad that was helpful. Any other questions about that so far? Okay, thanks for asking again about that one, Dana. It's definitely relative to what we're doing currently, since when we're thinking about concavity, it now suddenly gets mixed in with second derivative test. And if you're always concave up, this is the magic part, that means you truly have a local minimum. This is what concave up would look like in this region. Graph is always above its tangent lines. And for the second part of the second derivative test, it says, find a critical number. There it is, horizontal tangent line. That automatically means it's a critical number. If your second derivative is negative, let's take a look. It is. It's below the tangent lines in this region, so the second derivative is negative. You will have a local maximum. And take another look. That is truly a local max. So we'll say here, f of c is a local max. So that's the weirdness of the second derivative test. I always spend a little bit of time talking about it through graphs because, again, this is really harmful to the brain if we don't think about it a lot. Concave down leads to a maximum, and concave up leads to a minimum. Aside from that, the second derivative test is fantastic as long as calculating your second derivative isn't too much trouble. You just have to get around these weird reversals of directions. Well, we'll try out the second derivative test, but notice this right here. If the critical number comes out as 0, that's great. But if the second derivative of that critical number is zero, the test has failed. What we mean by the test has failed is it's inconclusive. There could be a local max there, or a local min, or neither. There's neither anything going on at that point. You have to investigate further, and sadly, that usually means use the first derivative test to investigate further. But this is the whole write-up of the test. We'll try out it next with a brand new problem. Any questions or comments or concerns or anything first before we give it a try? Okay, so this will be our last problem on these notes. And then we're going to go into our big application section on optimization. Oh, I think I forgot to zoom in. We're back to 130% zoom. So here's the second derivative test again. And for our example of a function, we'll use this one right here, h of x. Let's say a little bit more on part C, because that's going to happen on this problem. When it says failed, this means the test is inconclusive. And that just means no information can be gained. So let's try this out. We have a degree 5 polynomial, and we're on this step right here. We're looking for critical numbers, so we take h prime of x. That's a pretty fast derivative. That'll be 15x power 4 minus 15x squared. So there's the derivative part. For this part right here, we just go and set it equal to 0. And now we're solving that polynomial equation. Well, factoring is really our go-to method for anything like this. So let's factor out 15x squared. So here's h prime of x equals 0. In place of h prime of x, you have 15x power 4 minus 15x squared set to 0. At this step, we factored out 15x squared, and that's just a division process. We'll leave x squared here. Dividing it out from this location will leave a minus 1. Right where the red dot is, we can factor that one even further and say that this is 15x squared, and x plus 1 times x minus 1 is now set equal to 0. So we're at that step of just working with the critical number, but we pretty much have an answer. When factor by factor, the only way we get this to come out as true is x would have to be 0 right here on that location, or in this location, if x is negative 1, we'll have the equation balance as 0 equals 0, or from here, throw in a positive 1, and that's our set of critical numbers. So 0, negative 1, positive 1 are the critical numbers. Of h, since the original function is now h, not f of x. So after dealing with the critical numbers, we have to go to this part next. So think of this as your step 1. We take the derivative, set equal to 0 and solve. But if we're using the second derivative test, that's our natural step 2. We're going to eventually need the second derivative. Let's call this step 2. At step 2, we're calculating h double prime of x. So 4 will come down, multiplying 15. We have now 60 x cubed. Here 2 comes down, multiplies, and we have minus 30 x. So we've got the second derivative portion all set up. The last thing we're going to analyze is, notice the value c here. It means we're taking our critical numbers from this list, and because it says f double prime, we're throwing them back into our function in step 2. Some color coding probably is going to help out at this stage. Let's use blue for the critical numbers. And here's what step 3 looks like. Take h double prime at any critical number. Let's just start at 0 and see what we get. So at 0, we're going to get a 0 here and a 0 here. So the whole thing comes out as 60, 0 cubed, minus 30 times 0, But now that comes out, it has a value of 0. We're in this situation. The test has failed, and that means at the critical number 0, we have no information whatsoever. It could be a local minimum, a local maximum, or neither, none of the above. So all we need to say here is, due to the 0, the second derivative test you could say has failed, and that's just fine. You could say it's inconclusive, it doesn't give any information. Let's just go with has failed. Well, nothing interesting going on with that critical number as long as we're only using the second derivative test. So what we do is just move on to the next. Plug -1 inside the function h double prime of x and just see what happens. Before we go and finish off the last two, any questions so far to this point? Okay, let me just grab that for a really quick reference. And now let's finish off the rest of these last two critical numbers. So still in step 3, this is really our last step. Moving over to -1, we do the following. H double prime at -1 equals, oh, I forgot, we need to look at our second derivative. We're plugging -1 into those values for x. So 60, -1 cubed, minus 30 times -1. This is going to turn into, well, -1 cubed is -1, so -60 here, plus 30 from here, gives us a value of -30. But if we say -30, that means we're in this situation. The second derivative came out negative, and so we have a local maximum. But we need to say what that local maximum is, so we go down below and say, this implies h of -30 equals, and notice how kind of tricky this is. We have the second derivative we're working with a lot. We have the first derivative that we worked with a little just to get critical numbers. But when we go to give the conclusion of a local maximum or a local minimum of h, we go all the way to the top, oops, didn't mean to do that, and use the original function, h itself. So there's always 3 functions on the table whenever you're using the second derivative test. That's why it's a good idea to always label your functions as h of x, h prime of x, h double prime of x, just so you don't get mixed up with all that stuff. So let's put down our function just for a quick reference. H at -30 means we're taking, excuse me, I think I made a mistake here. That should have been, sorry for my mistake there. H at -1. So my mistake was the C there is the critical number, and we have a local maximum at C, the critical number again. So the critical number goes into that location. Sorry for that. Let me add a little more color coding just to connect those dots. Well, similar color coding. So we take -1, plug it inside here, and here's how it goes. 3 times -1 to the 5th power, minus 5 times -1 to the 3rd power, plus 4. Let me just continue to highlight those just to show where those numbers go. So altogether, this is -3 plus 5 plus 4, giving us a value of 6. Let's double check the second derivative. We got -30, which is less than 0. So now we can say this is h of -1 equals 6 is a local max. So if we were to plot the function, this one right here, we should see a maximum on that function when we're at x equals -1. So that's 2 critical numbers down, one last one to go. Any questions with this conclusion here? Okay, so there's really 3 answers that we're giving to this. This is answer 1. second derivative test has failed at the critical number 0. This is answer 2. We found a local maximum at -1. The local maximum is 6 itself. And now we'll plug in the critical number 1 into the second derivative way up here and get our third conclusion. So here's how the last step goes. Just move some stuff around. H double prime now at +1 equals 60 times 1 cubed minus 30 times 1. Same style of color coding just to show where the 1 came from. That was the critical number. This time we have 60 minus 30, giving us a value of 30 altogether. So we check our list on the second derivative test. If we got a +30, we're in this location for a local maximum. So let's go greater than or equal to 0. That then implies, well, we have to find the local maximum at C. The C it's referring to is the number 1 right here. So we find the local maximum by going H at 1. Now this time it's the original function. 3 times 1 to the 5th power minus 5 times 1 cubed plus 4. This is just a 3 minus 5 plus 4. So that comes out as a 2. And that's going to be our local max, or excuse me, a local minimum. It's always easy to get mixed up on this. So we'll say here, H at 1 equals 2 is a local min. So that last final conclusion there finishes off the entire second derivative test. Again, another box just to show what our official answer is. And that's how the test goes. Well, we did, folks. That's running through the first and second derivative tests. Any questions at all getting through this problem? Okay, while we're thinking about this question, again, we have to show these kinds of steps whenever we're doing a quiz problem, an exam problem, when we're working in WebAssign. But when we're doing our homework in WebAssign, we always have extra tools to see if our understanding is in the right direction. And the big extra tool all the time is usually just a graphing calculator. So let's see if our conclusions really pan out. H of x equals 3x power 5 minus 5 x cubed plus 4. Took a moment to actually type in. Looks like we do have a local max. We have a local minimum. Let's see what our conclusion said. We said here, H at -1, giving us a value of 6 is a local max. And yeah, that was the case. 6 is a local max in here on the graph. We said something else though. We said at 0, the test has failed. It's inconclusive. Looking over here, that makes sense why. The function is always decreasing even through 0. There's neither a local min nor a local max whatsoever in that location. And then finally, the last thing we said was, let's see here, H at 1, giving a value of 2, has a local minimum. Does look like a local minimum, and yeah, it's at value 2. So our conclusions check out. The only thing we didn't have any information on is where the test just totally failed and became inconclusive. Well, that's the rundown of the second derivative test. Any questions at all, folks, before we go on to the next section to apply these tools? Okay, let me get this all saved up, and we'll take a look at what's going on in section 4.4. Always kind of like a small mental break as we transition to the next set of notes. Okay, so we're finally now in section 4.4, optimization. To a lot of people, if you're talking about the differential calculus, doing derivatives, this is the most important application. That word's worthy saying here just on the notes. This is the most important application of derivatives. And it's something we've been hinting at a long time. Whenever we have a derivative coming out of zero, it looks like we could have a minimum or a maximum, and that's going to help us do optimization. So all the problems here are optimization kind of problems. We're looking for an absolute max or an absolute minimum. Example one is silly. This one you can solve pretty fast. A lot of people reading it probably already know the answer. The answer is you just divide 15 by 2 and then multiply them together. That's the smallest possible answer. But we're going to do example one, taking all the steps just to show how it goes in a simpler problem before we get into these kinds of problems. We'll look into photosynthesis. This is a model for maximizing the rate of photosynthesis. Next one, we'll be looking at something in, looks like consumer science. We're trying to minimize a cost of something we're trying to build. Then we'll take a look at a search function for pharmacokinetics on when, say, blood alcohol might peak. So several biological examples and a couple just routine number type problems like this one and example 3. So example 1 is the easy one to get started. But the trick with all these problems is we have to be actually really careful when we optimize. The thing that goes wrong is we get really good at this step. We take the derivative, we set it equal to 0, but once we do that, that critical number may or may not actually correspond to a local minimum or a maximum. So we always have to do a little bit more work. So that's why it says show all steps using the second derivative test. That's going to be the expectation as a quiz problem. So same again as an exam problem. So it's a good habit in doing these problems in the same kind of way when you go to do them in WebAssign. And the WebAssign for this section is highly kind of matched up with the kind of problems you'll see here on these notes as well. So this is like a strategy guide to help out with the homework all at the same time. Also, when you read the second derivative test, we just got done using it, but this one has a fine adjustment to it. The old second derivative test that we just used was for local minimums and local maximums, but this one is for an absolute minimum and an absolute maximum. So here's the adjustment. We find the critical number, that's the yellow part here, setting the derivative to 0. Then, if we have this part right here, if the second derivative is positive at x, for all x in the domain, then we actually have an absolute minimum, a stronger conclusion. Likewise, if we find a critical number, but we know that the second derivative is always negative for all x, not just at the critical number, it means we have an absolute maximum, not just a local maximum. So it's this part right here where it says for all x that gives the absolute minimum, and for all x here is what's giving the absolute maximum. Any questions, folks, with those 2 tweaks here that are in highlighted? Okay, well, here's how this problem starts. I guess we have to read it at some point. Example 1 says, the sum of 2 positive numbers is 15. So already from that write-up, we should just start defining variables. Let's say, let x, comma y, be 2 positive numbers for which it says the sum of them is 15, so that just means take x plus y, and we have a value of 15 altogether. This equation that we just built is sometimes called a constraint equation because it puts a constraint on what x and y can be if they're positive and they're forced to sum up to 15. So let's call this the constraint equation. So now the next part of the statement says, what is the smallest possible value of their sum of cubes? This is the quantity that we want to optimize. So we'll say down here, when it says smallest possible, we want to minimize the following. Well, we want to use calculus, and so the thing that we want to minimize should be a function. So let's call this f of x equals, But we also have to make the function match up with the question. It says sum of cubes, the sum part is adding things together. Of cubes means we're taking x cubed plus y cubed. So we're trying to minimize that function using this here as the constraint information. Well, that's our setup at the moment, but if you're looking at this right here by the red dot and feel slightly uncomfortable, I'm with you. That's a legitimate function, but it's a function that takes one input x. Yet there are two potential variables, x and y on the right-hand side. That means one of them has to be eliminated. Probably y if we set f of x. So our next step is to go back to this equation and solve for y. So that has to go. Let's say here, just for the notes, write f in a way that uses only one variable. So we're going to eliminate this y some way, somehow. But that's not too hard to do. We can go over here and just solve for it. We can say subtract x from both sides. Y is equal to 15 minus x. So there's our y. We'll plug it right back in there. And now we have an honest function. So f of x is now equal to x cubed plus 15 minus x cubed. So we've got a function. Sometimes this is the hardest part about the problem, just coming up with the function that you're going to optimize. And other problems just give you the function. So there's a lot of variety to these kinds of problems. But now that we have a function, let's call this step 1. Solve f prime of x equals 0. That means we're using the second derivative test to make this happen. So here's our function f. Differentiating is not too bad. We'll write f prime of x equals, on the first term, we'll get 3x squared. On the second term, this one is now a chain rule derivative. So let's work out this one carefully. Inner function is 15 minus x. Outer function is the power 3 function. So differentiating means first 3 will come down. New power on that group is power 2. Multiply by the derivative of whatever is inside that group, and it's 15 minus x. Notice that if we forgot the chain rule on this, our answer is extremely close because that derivative right there by the red dot is just a -1. So your answers would look very, very close. You would just be wondering if you forgot the chain rule, why there's a negative on the next step. It's for this reason right here. Well, any questions, folks, on this chain rule setup or any other element so far? Okay, let's continue to run through this derivative. We have 3x squared plus, oh, and I should have said plus, I already forgot we've got a minus going on. The derivative of this is -1, so I'll just put a minus right here for that -1. Then copy 15 minus x squared. So we finally have a derivative. We need now to set equal to 0 and solve. So there's us setting it to 0. Solving this thing is kind of a chore. It's going to involve expanding this out. So let's start by copying over here, 3x squared. Nice 3 times. Foiling this means first take 15 times 15. I think that's 225. Then it'll be 15 times x twice, 15 times -x twice, so it's -30x. Finally, -x times -x will give us positive x squared. So that's just the result of foiling out this quantity here by the red dot. Next step, we need to distribute the -3 into that group. So we'll get 3x squared minus 675 plus 90x minus 3x squared equals 0. This is a degree 2 polynomial equation, which usually means you have to factor, but it looks like a nice miracle occurred on this one. I didn't mean to make that one as big. Let's tone this pen down. It's supposed to be a cancellation pen. This and this will cancel off, so that helps us. Now it's just degree 1. So we can add 675 to both sides and say 90x is 675, divide by 90, and x is 675 90ths. That deserves a calculator. 675 90ths is a 7.5. So we found a critical number, x equals 7.5, is the critical number of f. Well, that's our step 1, folks. We found our critical number. Our next steps is just going to be maneuvering through the rest of the second derivative test. Let's take a screenshot and walk along with it. As we go to the next step. Any questions or comments so far, folks, to this stage? Okay, so we've got f prime of x somewhere inside here. Let's see if we can resolve what this worked out to. So we had f prime of x down to this step. But at this step, we simplified and got to here. So if I was slightly less lazy and labeled all of these as f prime of x, just for extra emphasis, then we can say down below here, f prime of x, just as a reminder, is equal to negative 675 plus 90x. We need that right there because in the second derivative test, this is step 2, we go to calculate this part. We need a second derivative next. So here's step 2. We calculate f double prime of x. That's not too bad of a computation. We get 0 here and 90 here. That means the second derivative of x is constant. It's always 90. It doesn't depend on x. And we can write this out next. It's 90, which is greater than 0, for all x. Doesn't matter what x you pick, that's the result. And saying this part right here is important in a way because it reminds you, if you had the second derivative positive for all x, you have an absolute minimum next. So we just need to state what that absolute minimum is going to be, writing out our conclusion. So here's step 3. Coming in. Well, we might have to use our original function, but let's read the original instructions once more. It says, what is the smallest possible values of their sum of cubes? That means, yeah, we need to use the original function right here to find that smallest possible value. So here's our original f of x. We had to design it ourselves, so that's ours. Let's maybe just throw it here as well, just as easy reference. Here's f of x. Now in step 3, we can now make our big conclusion. Because of bigger than 0, and because this happens for all x, we can now say the smallest, we're saying smallest because we found an absolute minimum, the smallest possible value of the sum of cubes is, and let's give it a little bit more space. I'm always kind of amazed at how much space we need. F at a certain value. So let's take another look. It says f of c is an absolute minimum. C came from over here, the critical number. And so somewhere we wrote out the critical number. There it is. That gets plugged in. Let's use yellow for that portion, just to emphasize and connect the dots. The smallest possible values of the sum of cubes is f at 7.5. That means we're plugging 7.5 in these two locations. Whoa, that's weird. I'm not too sure what causes that. 7.5 cubed would go here, plus 15 minus 7.5, cubed would go here from that location, x. So just two more computations. 7.5 cubed plus, well, this is also 7.5 cubed, so you can just say times 2. But if you like seeing it written out verbatim, just for the sake of being sure, that's what it came out as, 843.75. So that's the application of the second derivative test. Word of warning, the second derivative test isn't always the best test to use. Sometimes it's fantastic and saves you loads and loads of steps. Other times it's like your worst nightmare. You never want to look at it again after using the second derivative test. So maybe the last final parting thought on this is, let's say here, with our problem now complete, we found the smallest possible value, their sum of cubes, 843. But the takeaway point here is only use the second derivative test when f double prime of x is fast to calculate. Otherwise, it just really isn't worth it, to be totally honest with you. This test can take a lot more work than you would imagine in the case where the second derivative is a hard computation. But if our function f prime was this, the second derivative was basically easy as possible in a certain sense. So this is the type of problem that makes a really good use of second derivative test. I'm mentioning these last bits here in purple each time we do this problem, since when we go to do these as a quiz problem or an exam problem, it's really up to us if we're going to use a second derivative test or the first derivative test. The problem will indicate the best path, so we have to decide what makes the most sense to ourselves. Well, we did it, folks. That's the total conclusion to our first problem, finding the smallest sum of cubes. For the next one we're going to take a look at, we'll be using the first derivative test instead. Any last final questions or thoughts on this one? Okay, keeping the second derivative test in mind, let's take a peek at the next problem. It involves this function right here. If you differentiate that once, you already have to use the quotient rule, and it becomes a little bit more complicated than it already is. If you have to differentiate it twice, it's a hard derivative. You'll be there a while, and you still have to run through the second derivative test. This is a problem where the first derivative test is a really good idea, only because derivatives are already hard to calculate. So we will be using this test to get through this problem. Like before, this is a first derivative test that's been tweaked a little bit. It's for absolute extreme values. And the change is, if you have the derivative positive for all x on one side, when x is less than c, and you have it negative for all x on the other side, where x is greater than c, you have an absolute maximum. Switch those inequalities around, and you have an absolute minimum. But we resolve both of these really by just going to a number line and seeing where it's increasing and where it's decreasing. So that'll be the next test we get into. This one, unfortunately, I don't think we can solve in about 7 minutes. So this will be our first problem when we come back on Wednesday's class. Well, any last questions or comments then, folks, before we call it a day here? Okay, well, that's all I have for everyone today. I'll be back on for office hours at 3:30, so see you all later, unless I see you back on there. Have a great day.